All right, didn't get any emails or requests for any questions to be answered, so I'm gonna keep the chat open for about 5 minutes. I need to just check a few things online. But again, these are office hours. These are not lectures. They are not meant to convey any information that isn't already on the website. So if you got questions, please send them in advance. The only comment I am going to make, now that people have finally gotten the lab kits in, I've started putting in the lab grades. This is based on the first three labs. There's still a couple like the KSP labs that are kind of outstanding. But if you looked in the grade book today and you're like, wow, my grade really went up, it's typically what happens with the lab grades is that drives you up. So keep in mind the labs were 25%. It counts as basically 2 exams in the course. So lab grades should be pretty good for this course. It's a home lab kit. The lab practical really is just kind of a summary of the earlier labs. You don't even have to do experiments to conduct that to get that grade. So I'll try to update the lab grade every week. No promises, just because it is kind of a daunting process to get it off a WebAssign. But again, the lab grades are up. That's probably why a lot of you saw your grades go up this weekend or this morning when I posted the lab grades. So yeah, keep an eye on that. So again, I got the chat menu open. If you got questions, answer them. Otherwise, I'm just here to answer questions. Got a question. I came across KC while looking in the textbook. Is this essentially the same thing as KQ? So all KQ. So a KQ is just our general expression. And then within the umbrella of all the KAQs, there's a whole bunch of sub KAQs. So when we say Ka, it's a weak acid. Kb is weak base. KSP is solubility. Um, Kw is water auto dissociation. And you've got KCs. You've got a long list of them. So anytime you see this big K with a subscript, it's always an equilibrium constant. It's just that usually what we'll do is we'll see little subsets of these that are designed to specify. So if we have a weak acid, it implies that we're looking at this equilibrium. Weak base is going to have a base solubility. When it comes to solubility product, we've got some anions and cations in equilibrium. Kw is always H2O going back and forth to H plus and OH minus, and we're going to talk about it a lot more when we get to acid-base chemistry. So yes, they are the same thing as KQ. They're just special subsets. So all these Ks are little subscripts. They're all KQs, but not all KQs. You know, Ka and Kb aren't the same thing, but they are both equilibrium constants. They're special subcases. And the structures we discuss amongst ourselves, like which ones we think are the most useful ones to introduce you to. Kc, I don't know off the top of my head, but Yeah, you're welcome.
So do you think, like, is marketing definitely what you want to do? Do you think you need someone more experienced with it? What do you think? Wow, that's awesome. I mean, there's so many options out there, but is it a, I mean, if you had decided, I assume you don't want to come from a second marketing internship, keep it private, but if you had decided, like, by this point in your second internship, maybe I don't like it as much as I thought I did, like, that's still beneficial to me. So that's great that you're enjoying it. Absolutely. So we are, so my team is kind of revamping the way we work for at least this fall. I assume we'll probably do it all through spring just to see how it really works. But we have historically been a Wi-Fi school, like that's our first line, and we recruit for every function that goes through our school. We are switching to be first line by discipline, like we're a PE class. And then, but we are still the channel managers. And that's something that our school union gave us to not forget that term. So since we're still the channel managers, like our first year is we'll learn our functions, and then within that function will if there's more of us in the main function. So I'm going to be learning PA. So there are two of us that are learning PA, and we're allowed to have 9 different PA spots. So then the two of us will still always run schools, like we're union tied, but still at those schools we're only going to focus on CX recruiting instead of taking on all the different functions that go with those schools. So I'm really curious. We are, and I've done this since in kindergarten, and we've always been just an online school covering all functions. So I'm really curious how it's gonna play out. Um, I think it will be good in the sense that that way we can really be a deeply dive on, okay, who does this have, like why is this overload of that function required? And how can we really dive deeper on learning that specific side after school? But then it's just strange from the school side because obviously we build relationships with people across the schools. So I think it'll, and some schools are different. Like at UNC, we pretty much work with my internal contact at UNC are pretty much a business school and a computer science department, and then the UC University Group. Those are the three areas where I do the most. Um, so it'll be, I think, pretty easy. So like I'll
Any
have
other
some
questions out there?
team at a business school. And what we're doing with corporate functions is the way my team is dividing. So some of us are taking CX, some of us are taking engineering. There's and some of us are taking I think corporate functions is also quality. So basically everything that we recruit for at a business school is
Common question. Can you go over this problem in the notes? I understand how the values are being attained, but I was wondering if you can get an explanation to reinforce my understanding. So which... stop it. Hold on, it's logged me out of Blackboard. So which question in particular? Like, do you have a slide number? He says as he stalls for time as he tries to download the notes. All right, so gas, we have a gas mixture problem. So let me see if I can find it in the notes. I guess this is off the thermodynamic slide. So off the bat, all these problems are going to start with delta G equals delta G naught plus RT ln of Q. And I'm going to try to find the problem in the slides, but this is looking like a thermo problem. Nope, equilibrium. Oh no, it's even really hard on my end too. So our expression for Q here is, so KQ equals Q only at equilibrium, but we're still going to have, let's see here, it's CO, O2 going back and forth to CO2, 2 there, 2 there, and we've got, the pressure is 1 atmosphere, 101.325 kPa. We have temperature is 800 C. And we've got our mole fraction here is 0.5. Zero 0.24 and 0.26. So, and then the delta G here is minus 257. So the expression for Q, easiest way to do Q is the same way you set up KQ. So you got concentration of CO2 squared over the concentration of CO squared concentration of O2. But we had the pressure dependence. And so if we look at the pressure dependence, the quick way to do this is the mole fraction of CO2 squared with mole fraction of CO times the CO squared times the mole fraction of O2 times P naught over RT. And we've got 2 moles of product gases and 3 moles of reactant gases. I really hate to erase this, but I'm running out of space. So back it up in the video if you don't know what the reaction is. So if we simplify this, we get Q equals mole fraction of CO2 squared, mole fraction of CO squared, mole fraction of O2, P naught over RT to the negative 1. So this is just a number. All you've got to do is just stick in the information it gives you. So it gives you the mole fraction of CO2 is 0.26. Mole fraction of oxygen is 0.24. Mole fraction of CO is 0.5. And the P naught here, 101.325. The temperature here is going to be 1073 Kelvin. R is going to be 8.314. So when I find Q, that is 0.26 to the second divided by 0.5. So here I get Q to be 99.19, trailing on and on. So really, it's just kind of bringing, these problems bring everything together that you've been covering for equilibrium and thermodynamics. So expression for Q is just the statement of what Q is, squared all over this. We can use the substitution that the concentration of I, mole fraction of I, P naught over RT. Substitute that in all in, but you already kind of know this for the pressure dependence for... Okay, so for any equilibrium expression, this is kind of a shortcut. I know there's a lot going on here. So we talked about earlier about how to do the pressure dependence, and I think it's in the notes about how to do the pressure dependence for an equilibrium reaction. So if you want to know the pressure dependence, it's moles of product gases minus moles of reactant gases. So the two here, oh man, I really wish I had more space. So we have CO gas plus O2 gas goes back and forth to CO2 gas. We've got 2 moles of product gases, so that's where that 2 comes from, and we've got 3 moles of reactant gases, 2 moles of carbon monoxide, 1 mole of oxygen to give us that 3. But this is just the shortcut for finding the pressure dependence of KAQ. So if I ask you to find the pressure dependence of KAQ, you could take this shortcut, everything that's a gas, replace it with its mole fraction, and multiply it by P naught over T raised to the moles of product gases minus moles of reactant gases. Q is still going to hold the same pressure dependence. It just isn't going to numerically equal KAQ because we're not at equilibrium. But if you do all this, plug in what it gives you. Q, I think I got was 99.19. R here, 8 point, in this case 0.08314 kilojoules per mole. Temperature is 1073. You'll end up getting delta G. So this problem has a lot of moving parts, but they're all built on the previous parts from earlier material. Yeah, you're welcome. This would represent the super hard extreme. I don't think I give any exam questions that are this difficult. This is definitely the extreme of these types of problems because there's a lot of places where you could go wrong. But if you can do this type of problem, you're more than set for that part of the exam. Actually, it's going to be both depending on where you are. So if you're working with the, so the question here is R 8.314 or 0.008314? And then in the notes, it goes from 8.314 for working with Q, and then goes to 0.008314 for finding delta G. Does it matter if they're switched or if we use the same R constant for both? So the thing here is the units. So there's two values of R. If we have 8.314, this is kilopascals times liters over mole Kelvin. And the 0.008314 is kilojoules per mole Kelvin. And this is why I prefer students to work with this R, because the only thing you have to do is memorize the number and the position. If you were to go multiply this by 1,000, you would get 8.314 joules per mole Kelvin, which numerically, by units wise, is equal to this as well. So we have to look at the context of where we're using R. In this case, R is next to pressure. And so since it's next to pressure, we need to use this kPa liters moles Kelvin, because we're working in units of liters per mole to get the concentration. Up here, kilojoules is in, or delta G is in kilojoules per mole. So since we're in kilojoules, we're going to want to work with this R constant. So if we're working with any type of thermodynamic values, delta G, delta H, delta S, R is going to take the 0.008314 because we're working in units of kilojoules per mole. If we're working with gases, and which is going to be the case we're working with Q, that's where the 8.314 is going to show up because it's got units of pressure in it. But it does matter where you use them because you will get radically different answers. Now, some instructors do teach delta G and delta H in joules per mole Kelvin. Don't learn it that way, because no book works in joules per mole Kelvin. Well, like nothing above a freshman textbook works with joules per mole for delta G and delta H. You're welcome. Thanks for the questions. Okay, so this is the cool thing about extensive reaction. And this is why ice tables are so much better solved with extensive reactions. So, depending on who you had for Chem 1, they may or may not have explained what a reaction coordinate is. So, let's say we have our reaction from before TCO gas plus O2 gas goes back and forth to 2CO2 gas. Now, we could always explain. All right. All right, answer that question. All right, so basically, there are two ways people approach solving reactions. And one way is they try to think about it like I need to solve for moles of every single component individually. But extended reaction is basically defined as a unitless measure of how far a reaction gone, how far a reaction has gone. So it just says the reaction has gone so far, but it hasn't specified like how far that is in terms of a specific reagent. An extended reaction can take pretty much any value, but the extended reaction has the property that if we take the extended reaction and we multiply it by a reaction coefficient, we'll get moles of that compound. So if we want to figure out the moles of CO that reacted, we would just multiply by 2. If we want to figure out the moles of O2 that reacted, we multiply by 1. If we want to figure out the moles of CO2 that react or that are produced, we just multiply by 2. And this is the power of the extent of reaction, is that we can always scale the extent of reaction to whatever reagent we're interested in. So for the IC table, this is why we would prefer to work with it. So even if we're working in molarity, they're all in the same volume, so we can get away with using that trick as well. But let's say we had some starting amount. Let's say we had 1 mole of both of these, and we want to know how much CO2 we produce. Well, we could sit back and say, well, let's define the moles of CO that react. And then we'd have to do this coefficient, this unit conversion between A and oxygen, so you get 1/2 here, and you'd get 1 here. And you can do that, but it's a lot of work. The other option, which we do to simplify it, is that we just say it's extended reaction times the reaction coefficient. And you'll see in the notes, we just define extended reaction as positive for products, negative for reactants. There are debates on this. I prefer this because it takes a lot of thinking out of setting up the ICE table. But then, because we have this definition that the X times the reaction coefficient gives us moles of whatever we're working in, the units automatically work out here. So extended reaction is basically, again, to kind of back up, extended reaction just says it's just a unit of how far a reaction went, but it doesn't specify is it CO, O2, or CO2, but just by how it's defined, if we just multiply it by the reaction coefficient, we automatically scale that distance as to whatever we're working with. Another way to think about it is, let's say you walk across a room, and we know that you go the length of the room, but the room can be measured in inches, feet, meters, centimeters, kilometers, millimeters, all of that. It's the same distance across the room. The actual numerical value depends on what units we're working in. So we would just say you went across one room and then multiply by however many feet, inches, centimeters, meters, kilometers correspond to that given room. And reactions are kind of the same way. X just says the reaction went so far, but if we multiply by, we know carbon monoxide in this case reacts twice as fast as O2, so we expect it to go twice as far, so we would just multiply that distance by 2. So it's kind of like a nice little, by the way it's defined, it's a nice universal variable we can use to describe how far the reaction is. and it's got some nice properties associated with it to make it easy to convert it from extended reaction to whatever we're looking at. Now, there is a hidden advantage to it, and this shows up a lot more with reaction kinetics. The concentration of any species can be defined as its starting concentration minus its reaction coefficient times x. So the change in concentration of I is just dx dt times nu I. And because of that, we can convert any reaction into an ODE, an ordinary differential equation. So it can always be solved. Not particularly useful in this class because we don't do calculus, but yeah, I hope that kind of answered your question. Oh, and I should probably explain the plus minus configuration, plus minus thing too. Build the IC table again. So we're just going to start with numbers. So why do we do the plus minus configuration? There are actually two schools of thought on this. One school of thought says that reactants are always defined as negative and products are always defined as positive, and that's the one I was taught, and I think it's the most useful. And the reason this definition shows up is to say that, well, we expect the reactants to disappear and we expect the products to form. So since this C row here is a change, we expect there to be a negative change, a loss of CO and O2, and the production of CO2. But this all supposes that this reaction, it's Q. Pen's finally dying on me. It all presupposes, there we go, that Q is less than KEQ. And because it makes that assumption, we can be wrong. And what will end up happening is that we end up with, so we'll say it assumes, but if Q is really greater than KEQ, we'll get X is less than 0. So this just means that the reaction ran in reverse. If the extended reaction is negative, it means that we took products and converted them to reactants. So the upside of this is that it makes it really easy to define the changes in this table. The problem is that you can end up with negative roots, and you just kind of have to verify that your roots make sense. So with any quadratic, you're going to end up with a positive or a negative. You're going to end up with both positive and negative roots. You need to pick the root that guarantees you that the concentration, the numerical value of concentration, is always greater than 0. Now, the other school of thought says that you need to figure out what Q is. So you take the starting concentrations here and you plug them into Q. And if Q is less than KQ, reactants are negative, and your products are positive. And if you get Q is greater than KQ, you just flip it. And so the change here is defined by doing this calculation. Now, the reason I don't like doing this is that this is a lot of work, actually. And the problem is the only thing that it does is it guarantees that the real root is the x that's greater than 0. So you always know which root to pick because it's the one that's positive. That said, you're having to do a lot of work to calculate Q, and if you're going to do that, yeah, it saves you issues of determining which root is real, but honestly, if you just do it this way, your ICE tables never change. And because they never change, you can kind of just go ahead and build the ICE table for every single problem. This takes all the thinking off the back end of solving the IC table. You know that the positive root is the real one. By defining the change as negative here and positive here, you have to do a bit more thinking on the back end to say, okay, which of these roots are probably real? So you have to look at the concentrations to figure out which of the roots gives you a negative concentration versus a positive concentration. That said, I'd rather do the work there because generally what's going to happen, especially at this level, you're going to get a positive and negative root. And odds are the positive root is going to be the one that works. You just need to check it. If you get it 2 negative roots, it's really easy. Plug in one of the roots. If you end up with negative concentration, then the other root's the solution. But again, both skill sets work. I mean, you're not necessarily more right or more wrong for doing one or the other. I just find this definition a lot easier to work with. And particularly when we start talking about acid-base chemistry, this always ends up being true. But extended reaction is super useful. It solves a lot of problems for us in terms of solving these problems. And actually, yeah, you're welcome. So the way I introduced this concept in Chemistry 1, which may help you see it a little bit better, is when we do limiting reagents. So let's say you had, just like your problem, 2CO gas plus O2 gas goes, instead of making reversible, we're going to make it irreversible. And let's say I give you, we'll do an easy one, 1 mole of each. So you know off the bat which one's the limiting reagent. It's the carbon monoxide. So one way students are taught to solve these problems is to say, okay, figure out your moles of CO2. So we have 1 mole of CO, and we produce 2 moles of CO2 for every 2 moles of carbon monoxide, and for every 1 mole of O2, we produce 2 moles of CO2 and 1 mole of O2. And you can see that this produces 1 mole of CO2, and this produces 2 moles of CO2. So clearly this is the limiting reagent. But the thing is that the only thing different between these two is this first half here. In the end, we're going to multiply by the 2 moles of CO2. So really, it doesn't matter what this number is. We could put any number in here, and we would still get the same answer, that the bigger number represents the non-limiting reagent, the smaller number represents the non-limiting reagent. So let's just get rid of this altogether. So we just do 1 and 1. And what we end up getting when we finish is 0.5 and 1. There's no units on it because our moles of CO cancel out. And this is your extended reaction. It says the extended reaction here is 0.5, and the extended reaction here is 1. So this goes 0.5, whereas this goes 1. Since this doesn't go as far, this must be the limiting reagent. And the power here is that now that we know that X is 0.5, the extended reaction is 0.5 for this, we have the definition that the concentration or moles of anything is its starting concentration minus the extended reaction times X. So for our CO, we start with 1 mole, its coefficient is 2, multiplied by X, 2 times 0.5 is 1, so that's 0. For CO2, we start with 1, its coefficient is 1, we multiply by X, which is 0.5, we get 0.5. For CO2, we start out with none. It's a product. Its coefficient is 2 times 0.5 gives us 1 mole of CO2. So you can rapidly calculate all the other different moles just because they all have this extended reaction times the reaction coefficient, and we know their starting amounts. So in terms of Chem 1, what's really handy to do to figure out extended reaction is just, or figure out limiting reagent, is just go through all your starting reagents and divide them by the reaction coefficients, and that'll give you the extended reaction based off of that particular reagent. The smaller number is your limiting reagent, and now that you know that that's the extended reaction, you can go through and calculate everything else. And then this kind of shows up with equilibrium, because equilibrium we don't go to completion. So we just can't divide our starting amounts by by the reaction coefficients because they're not completely reacted away. There's always a little bit left over. But we can kind of see this idea popping in to say, well, we don't know how far it went, but if we have an extended reaction, that extended reaction is just kind of a placeholder. It's how far the reaction went, but we don't know how far it went, which is what we're solving for. And I realize that was a really long answer to your question, but that's actually more of its origins is extended reaction or a limiting reagent. And then you can kind of step away from the limiting reagent and say, well, let's say I don't know what the limiting reagent is, but I want to know how far the reaction went. Well, that by definition is extended reaction, just how far a reaction went without specifying which reactant or product we're talking about. Yeah, a lot of instructors teach dimensional analysis, and honestly, at the Chem 1 level, that's really all you need to know. And I introduced all three concepts when I teach Chem 1, as I say, okay, here's extended reaction, here's finding a product, and here's converting from one reactant to another. And honestly, at that level, it's not going to change anything. But once you start getting to this level, it's like, okay, now extended reaction begins to be a bit more important. But the thing is that a lot of people take Chem 1, it's just a gen ed requirement, they just need a science requirement. Chem 2 assumes that you're kind of going into a chemistry related field, and then if you go into organic chemistry, it's probably a directly chemistry related field, not like tangentially related. But yeah, the extended reaction is so much more powerful. But it's also kind of an abstract idea. When you do the dimensional analysis, you can kind of see what it connects to. Extended reaction is a unitless quantity. It's abstract in what it's describing. But if you can make that connection as to what it's describing and it clicks, you begin to see why it's such a useful number to work with. Because it just scales. All right. Thanks for showing up, Dia. And yeah, I'll probably see you tomorrow. All right. Any other questions out there? I'll give you about another minute or two. If there are any questions, we'll just take off early today. All right. Well, thanks for Dia showing up and anyone else who's been watching. Again, with all these live streams, these are not lectures. These are very much office hours. So if you have questions, please email them in advance. Otherwise, I will see you later.